right, section 3.3. It's going to be easier than section 3.2. I don't think we need this. Turn it off for now. And it's actually going to start out with something that we've talked about part of before, but it's got an additional piece that we haven't. It talks about the word roots, about the word zeros. So if we have a factor, like we did back in section 3.2, x minus c, and it occurs more than once. So we haven't seen that part happen before. So if it occurs more than one time in the polynomial, while we mentioned, Kylie, you asked me, like, do we have to write it down a second time? And I said no, but it wouldn't be wrong if you did, right? If it occurs more than once, then we talk about it having a multiplicity, right? It's a multiplicity of however many times it occurs. So if it occurs 3 times, it has a multiplicity of 3. Okay, so it's just a phrase that we use to refer to it. Now, we're going to do a real straightforward one to start with, one that's already factored for us. X cubed times x minus 2 squared times x plus 4. And the reality is that the multiplicities come from their exponents. Okay, so there's no exponent over here. It's an understood 1. So those numbers and those exponent locations on the factors are my multiplicities. Now, ignoring the exponents, you can actually find the zeros. Namely, if you take x and set it equal to 0, x minus 2 and set it equal to 0, and x plus 4 and set it equal to 0, these are the zeros. So the x equals 0 is already solved. What is the solving? What do I get for x minus 2? What's x? 2. And what do I get for x plus 4? Negative 4. So we're supposed to state the zeros, which we did, and along with them we're supposed to state the multiplicities. So this is a multiplicity of 3 because the exponent is 3. This is a multiplicity of 2 because the exponent is 2. And this is a multiplicity of 1 because the exponent is 1. Is that okay? Now, the problem was friendly at the beginning because it was already factored, which is true. But does all the pieces make sense once it's in factored form? Okay. So the next example is not in factored form, but it does have just 3 terms. And while it isn't quadratic, it almost feels like it is because if you take a look at the terms, they're each decreasing by 1 each time. Right, I have x to the 5th, I'm trying to make this a little smaller, x to the 4th, and x to the 3rd. So the exponents decrease. There's no missing pieces like in some of the ones we did in 3.2 where there's an x term missing, right? So as we look at all 3 of these, is there anything common to all 3 factors that we can factor out in front? You can pull out an x to the 3rd. They all have at least 3 x's in them. And if I have x to the 5th and I pull out 3 of the x's, I'm left with x squared. In the middle, I'm left with 6x, negative 6x. And at the end, I'm left with 9. And then the part in parentheses really is a quadratic now, which means we can attempt anyway to factor it if it will. And it does factor. So how does x squared minus 6x plus 9 factor? My x's, what are my signs? Both subtraction. 2 numbers that multiply to 9 add to negative 6. They're 3's. And while this is written twice, it might actually be easier for us to think about the fact that it actually means that there are 2 of them, as in it's squared. You don't have to write that down, but you do need to recognize somehow along the way there that there are 2 of them and they're actually the same. At this point, it's in the same form that the first problem started out as. The multiplicities, I totally left my 3 out and wrote a 2. I don't know why I did that. Let's fix that. My multiplicities are 3 and 2. And I can set each piece equal to 0. So the first one is just easy, automatic. It's x equals 0. The other one is x minus 3 equals 0. So what does x equal? 3. What is the multiplicity of x equals 0? 3. And what is the multiplicity of x equal 3? 2. Okay, so you might be saying, okay, fine, you've got this extra little thing you're writing down about the power. What does it matter? Well, it actually matters, and it affects what the graph looks like. So these are some graphing facts about multiplicities. When you have multiplicities, there's several things that affect, and I shouldn't say when you have multiplicities, when you have a polynomial, there's several things that affect the graph. One of them is the degree of the polynomial as a whole. So if you have a degree n, you will have n roots. So if it's a cubic, you'll have 3 roots. So I alluded to it back in 3.2, but it wasn't part of what we were proving or thinking about specifically at that point. So 3 exponents, or an exponent of 3, you're going to have 3 roots. They don't always end up being x-intercepts. We saw that happen as well. Complex roots come in conjugate pairs. So remember at the very end we had that complex one that was 1 plus or minus I? So if you have 1 plus I, you got to have 1 minus I. They always come in pairs, and that should make sense because they come out of the quadratic formula that has the plus or minus in there, right? So yeah, they come in conjugate pairs. If the multiplicity is odd, so right where we had like x cubed here, right, an odd multiplicity, the graph actually will cross through the x-axis at that location, like it'll cut clean through. But if the multiplicity is even, like the power 2 or a power 4 or something like that, it will bounce off of it. So you want to imagine like kind of what parabolas do at their vertex, right? They bounce down and bounce back up. That's what happens on the x-axis, or upside down, bouncing up and then bouncing back down off of the x-axis when the multiplicities are even. So we're going to look at some of these graphing features, but it actually shows up in this section, but then it doesn't have you do a whole lot of graphing today. But it is interesting to work in the other direction as well. So if you take a look at these problems are working exactly backwards of what these problems were. On these problems, you started out with a polynomial. You were asked to find the roots and the multiplicities. On these problems, you're told what the roots are, and on the further examples of this, we're going to be told if they have any multiplicities. Okay, so here's what we have. We have a polynomial equation, real coefficients. We have the roots 2, 4, and negative 3. So this is telling me that x is equal to 2, x is equal to 4, and x is equal to negative 3. That's what it's telling me. Well, what does it mean? Well, if x is equal to 2, what's the factor? X minus 2. And if you can't jump to that just by thinking of it backwards like we were, that's okay. What you can actually do is you can actually just subtract the 2 from both sides. All right, this is x minus 2 equals 0. You can do the same thing with 4. X minus 4 equals 0. And with the negative 3, add my 3, and x plus 3 equals 0. Does everybody see where all those 3 came from? Okay, and then what we do is we take each of those 3 binomials and we multiply them together. So our function, we'll call it f of x, is x minus 2 times x minus 4 times x plus 3. That's the new information. The old information is what follows. We're going to multiply it out. Okay? So you take any 2 you want, it doesn't matter. I'm just going to take them in order. So we're going to multiply the first 2 together. But if you wanted to multiply the second one and the third one together, it doesn't matter. Just pick 2. And we're going to FOIL it out. So I've got x squared. My inner and my outer will typically add to the same, like they'll be able to combine. The inner is negative 2x, the outer is negative 4x, which gives me negative 6x. If you need to write it down to get to that point, do it. Negative 2 times negative 4 is 8. And then I need to take x squared minus 6x plus 8, and I need to multiply it through to x plus 3. So there's no fancy like FOIL FOIL for this. We actually have to distribute one piece at a time without a fancy acronym. But it's okay. What we're going to do is we're going to take x squared, and I'm going to distribute the x squared to the x and to the 3. That's how I do mine anyway, to keep track of them all. So x squared times x is x cubed, x squared times 3 is 3x. And then I'm going to do the same thing with the next term. It's negative 6x, and I'm going to multiply it by each of them. So negative 6x times x is negative 6x squared. And negative 6x times 3 is negative 18x. And then we're going to go with our last term. I've got my 8. 8 times x is 8x. 8 times 3 is 24.
Would the 3x be 3x squared?
Did I miss one? Yes, I missed that. Thank you. 3x squared. Did I miss anything else? I think the rest of the pieces are okay. Thanks for catching that, Kylie. All right, so I have x cubed at the beginning. 3x squared minus 6x squared is negative 3x squared. And then I have negative 18x and positive 8x, negative 10x. And at the end I have 24. So the function that I was looking for, like my final answer, is exactly that at the end. It's the distributed out, multiplied out version of all of those pieces. Okay, so the next one we're going to do is going to have imaginary pieces with it. This one tells us I have negative 9i and positive 9i. Remember, they occur in conjugate pairs, so it makes sense that if I have negative 9i, I have positive 9i. I'm going to have both of them. So on this one, I have x equals negative 9i and x equals 9i. And if I shift them, I have x plus 9i equals 0. On the other one's subtraction. So I have x minus 9i equals 0. Is that okay so far? I know there's i's in it, but they haven't done anything to us yet. They're operating just like the other pieces were. And then it's these two that end up being my factors. So my function, f of x, or whatever other name you want to call it, and it's x minus 9i times x plus 9i. And we're going to distribute it out. So when I multiply x times x, that's cool, I get x squared. But here's what I'd like for you to take a look at with conjugate pairs, because it always works this way. The inner conjugate pair is negative 9ix. The outer conjugate pair is positive 9ix. So what happens when you add those together? They cancel out to 0, right? That's why conjugate pairs happen every single time doing this, is because I can't have any i's in the final answer. I'm supposed to have real coefficients. No imaginary units should be there. But I do still have the last pieces multiplied, even though the inner pieces distribute out. I have negative 81i squared. But I squared is negative 1. So this is x squared minus 81 times negative 1, or x squared plus 81. Okay, any questions on that one? Now something weird is happening on the next one on C. What do you notice that's weird on C, based on things I've already told you? Ooh, there's missing a conjugate pair. But just because it's missing doesn't mean that it's really not there. It means that they want you to remember that it should be. So when you see the negative I there, you need to also include I as an additional 0. They're just giving you incomplete information that you have to complete. And now you have all those pieces again. So we have x equal 4, x equals negative I actually on the first one if I'm going in order. Not that it matters, but we'll put it in. And x equals positive I. We are going to shift each one of these. So this is x minus 4 equals 0. add my I, x plus I equals 0, and subtract my I, x minus I equals 0. So far, so good. Now we're back to doing the same thing we did in the last problem. We just have 3 terms, much like on the previous one. I have, come on, here we go, x minus 4. I have x plus I, and I have x minus I. Now I mentioned when we did this problem before that we could choose to multiply them in any order, and that's a true statement, and it's still true for this particular problem. But it's going to be a lot easier if you do the conjugate pairs together first. So I strongly recommend that you do that because the conjugate pairs will eliminate the i's, much like they did on part B, if I do them together first, and I do the x minus 4 last. So we're going to multiply out these two together first. So I have the x minus 4 at the beginning, and then I have x squared here. But the conjugate pairs show that the inner and the outer terms match, right? But with opposite signs, so they will be 0 when added. And then I have negative I squared. But I squared is negative 1. So this is f of x equals x minus 4. And it will be x squared plus the number 1. Because I squared is negative 1 and there's already a negative in front of it. So it will be x squared plus 1. And then I can actually FOIL out again because I still have 2 binomials, and that's why this is the preferred direction of multiplying these out. Okay, so I have x cubed, first terms together. My outer terms would be positive x. My inner terms is negative 4x squared, and my last terms are negative 4. If you want to leave it like that, that's okay. For those of us who are a little OCD, we might want to write them in descending order of exponents. The back of the book certainly will have it written like this. Any questions on that? Okay, we have one more problem, and I think we have just enough time for it. I'd like for you to notice on this one that I have another one that has an imaginary unit, but it's a little bit more complicated than the previous two that I've had. I have 7 plus I, right? They have to come in conjugate pairs, so what do I need? I need a 7 minus I as well. So there is one of these there. It's going to be in the problem. So I have x equals 7 plus I. I'm going to put the other imaginary piece next to it. So x equals 7 minus I. And I have x equals 3. So on each of the first two, I have to move not only the imaginary unit, but the real unit as well. So I have to subtract a 7 and an I from both sides. So this is x minus 7 minus I equals 0. And the other one I have to subtract a 7 and add an I. So it's x minus 7 plus I equals 0. And the last, of course, is simply x minus 3 equals 0. Now, there's nothing about the fact that it's not pretty. It's not easy because they're 3. Each of these are 3 terms, right? I mean, they just are. So these are my 3 terms, 3 factors that I'm going to be multiplying, but 2 of them have 3 terms in them. So x minus 7 minus I, x minus 7 plus I, and x minus 3. It is still far better to multiply out the ones that have 3 terms by 3 terms because the imaginary units will simplify. So I'm still going to multiply these 2 together. I'm not going to try and cancel things as I go, though. Like over here, when I notice the inside and the outside canceled, I didn't write them down. I'm going to have a hard time keeping track of this because 3 terms times 3 terms is going to give me 9 terms. So as I multiply out the two pieces that are currently highlighted, I'm going to get 9 terms. So I'm going to do like I did earlier, where I just take the x and I distribute it through everything. So I'm going to multiply my x through everything, then my -7 through everything, and then my -I through everything. So x through everything gives me x squared minus 7x plus 7I. This -7 through it gives me -7x, positive 49, and -7I.
Why is it x squared minus an x plus 7? If it's x,
Which one? This one? Oh, I wrote it down wrong. Thanks for catching me. I'm trying to move fast because I'm running out of time. I'm sorry. Plus xi. Are the rest of the pieces okay? The 7I at the end? I think that one's okay. It's okay. And then I have negative xi, or ix. I have a positive 7I, and I have negative I squared. Okay, so let me clean up what's inside of here, and then I'll pause. I'll let you guys watch the 30 seconds that follow or whatever, so we can get out of the hair of the next people. Lots of pieces cancel. Xi, negative xi. There's an I something missing. Where did my 7I go? Is that where I missed it? I missed this one too. No, that was okay. Oh, there they are. Sorry, there they are. Negative 7I, positive 7I. Cool. And then this one right here is -1, which makes it a positive 1 here. So at this point, I have x squared. Here are two -7x's, so that's -14x. And then I have a positive 49 and a positive 1, making it positive 50. The last thing I'll do after I pause and let you guys leave is I'll distribute the x minus 3 through and combine the pieces. So it cleans up, it simplifies, it's very nice at the end. It just has a lot of pieces to it in the middle. All right, so for the last part of this problem, we're just going to be multiplying out that x squared minus 14x plus 50 times x minus 3. I'm going to shrink this a little bit. Give ourselves a little bit more room down here at the bottom. So we distributed something kind of like this before. I'm going to take my x squared, distribute it through here, and then go on down the line. So x squared times x is x cubed. X squared times 3 is negative 3x squared. And then we'll do the same thing with the negative 14x. So negative 14x times x is negative 14x squared. The 14 times the 3 would give me a positive 42x. And at the end, I'm going to multiply my 50 through, so I have 50x, and I have minus 150. And then we'll combine like terms. So this is x cubed at the beginning. It doesn't always happen this way, although the couple that I've done have done so, where the numbers are beside each other, right? The negative 3x squared and the negative 14x squared, but whatever the x squareds are, you would combine them. So I've got negative 17x squared. And then I have the 42 and the 50, so that's 92x. And at the end, I have the minus 150. And at the end, it should also have the f of x written, or whatever your name is you've given it, at the left-hand side. And we'd have our answer.